Welcome. Today we're going to be talking some more about radicals that are found inside fractions. When we're talking about radicals inside fractions and we want to simplify them, we've got to do two things. Simplified means there's no perfect squares under the radical. Oops, here we go. No perfect squares under the radical. Only imperfect squares can be under the radical. So for example, if we have square root of 8 and we change that into 4 times 2, 4 is a perfect square, so the square root of 4 is just 2. So 2 comes out from inside the radical. Only the imperfect square 2 is left inside. The other thing that we have to know is that no radicals are allowed to be in the denominator of the fraction. So this is not simplified. Why? Because there is a radical in the denominator. And this is not simplified. Why? Because there is a radical in the denominator. We're going to deal with both of these cases today. All right, this one we've talked about before, but it's worth reviewing. If we have a radical in the denominator, there is a trick, a math trick that we use to get rid of it. We multiply it by the number 1, and we write the 1 like this. That's just the same thing as 1, right? Any number over itself is just 1. Now we just multiply fractions. Numerator times numerator equals numerator. Denominator times denominator equals denominator. Let's see what we get. Numerator times numerator, that gives you root 15. Denominator times denominator, what's that going to be? It's going to be the square root of 5 times 5. And the square root of 5 times 5 is just 5. No more denominator, radical in the denominator. Let's watch this trick. If you have a more complex denominator like this, look what we can do. Same strategy. We're going to multiply by the number 1, and we're going to write 1 like this. Okay. This is called a conjugate. Notice the relationship. This is 3 plus root 5. This is 3 minus root 5. Does this look familiar? We've done multiplication like this before. Now we do the same thing as we did up here. Numerator times numerator equals numerator. So let's take a look at what the numerator is. Okay. 1 times 3 minus root 5 is just 3 minus root 5. Very easy. Now the denominator, we've got 3 plus root 5 times 3 minus root 5. Is that a familiar pattern? Let's see what it turns out to be. We end up with 9 plus 3 root 5 minus 3 root 5 minus the square root of 5 squared, which is 5. Notice how these middle terms are going to become a 0 pair. You have 3 root 5s, you take away 3 root 5s, you end up with 0 root 5s. All right. Oops, that one shows you the answer. I'll give you this one. So if we have negative 1 root 7, we're going to multiply by 1. I'm going to multiply by root 7 over root 7. I'm going to end up with numerator times numerator. That's negative root 7 over root 7 times root 7. That's the square root of 49, or the square root of 7 squared. We take that perfect square out of the denominator. We end up with negative root 7 over 7. Answer. Try this one here. I'm going to do 2 over root 3, multiply by root 3 over root 3. Numerator times numerator equals 2 root 3. Denominator, root 3 times root 3 becomes the square root of 3 squared. There's a perfect square underneath the radical. We take that out. That becomes 2 root 3 over 3. Okay. Try the next one. Negative 5 root 5 times root 5 over 5. Okay. Negative, numerator times numerator is negative 5 root 5. Okay. Square root of 5 times square root of 5 is square root of 5 squared. Take that perfect square out, you end up with negative 5 root 5 over 5. What do we do now? We still have to simplify. If you have a fraction that has a 5 in the numerator and the denominator, that one can be reduced. Watch this. That becomes negative root 5. Okay. Let's try just a little bit more complicated one. 2 times 5 root 5. What do I multiply? Do I have to multiply by 5 root 5 over 5 root 5 or just root 5 over root 5? Just root 5 over root 5 because we're just trying to get rid of that radical. Numerator times numerator. Denominator times denominator. Remember there's an invisible 1 right here. Multiply the integers first. 5 times 1 is 5. Now multiply the radicals. Square root of 5 squared. This one comes out. Now you have, we need a little more space here. Now you have, I'll go back to green. You have 2 root 5 over 5, that's this 5, times 5. We took the square root of 5 squared out. Is there anything left in the denominator? No, we're done. So when we simplify this up, we have 2 root 5 over 25. Can I cancel here? The 5 and the 25? No, because this one is under a radical and this one is not. All right, I'm going to give you a couple more of these. Let's try 2 root 2 over root 50. Okay. Let's go ahead and multiply by root 50 over root 50. You could simplify this first. There is a perfect square in it. I'm going to go ahead and just multiply by root 50 over root 50. I end up with 2 root 100 over square root of 50 squared. What's going to happen here? Let's see. Perfect square comes out of the radical. Perfect square comes out of the radical. So in the top, we end up with 2 times 10. That was from inside. That was the square root of 100. Anything left inside the radical? No. And on the denominator, what do I get? I just took square root of 50 out, so I have 50 in the denominator. Now I have to reduce, right? Let's reduce with red. The 50 and the 10 can cancel. This ends up being 5, and I end up with 2/5. Let's try another one. Square root of 4x squared over square root of 3x. Now I could simplify this one right away because I see some perfect squares. The way I'm going to do it though is I'm just going to go ahead and multiply by square root of 3x over square root of 3x. Up here I'm going to end up with square root of 4 times x squared times 3 times x. And in the bottom, the square root of 3x squared. Okay. So in the bottom, I take out my perfect squares, these. That becomes a 3x in the bottom. In the top, I've got this perfect square, square root comes out. This perfect square, square root comes out. Square root of 4 is 2. Square root of x squared is x. What's left under the denominator, under the radical? Square root of 3x. Can I simplify? Can I reduce? Yes, I can. This x and this x come out. I end up with 2 square root of 3x over 3. Let's try this one. 2 root 3 over 5 root 6. All right, first step. Let's multiply by root 6 over root 6. I'm going to end up numerator times numerator. I end up with 2. And remember, I'm not actually going to multiply this out to 18. I'm going to leave it as factors. 3 times, how can I factor 6? 3 times 2. And on the bottom, I have 5 times the square root of 6 squared. All right, next step. Find some perfect squares. That perfect square comes out. This perfect square comes out. The square root of each of those. So let's begin with what we had before. We had a 2 on the outside in the numerator. We're going to multiply it by the 3 that we're taking out. And we still have a 2 left inside. That's the imperfect square. In the denominator, I started with a 5. And I'm taking the square root of 6 squared out. Square root of 6 squared is just 6. Do I have anything left in the under the radical? No. So now 2 times 3 is 6 root 2 over 30. Can I reduce? You betcha. This and this. 6 goes into, this becomes a 1. This becomes a 5. I could write 1 root 2, but I'm just going to let that 1 become invisible. We're going to call it root 2 over 5. Okay, last one here. Square root of 3n over 3 times the square root of 5n cubed. All right, I could start by taking a perfect square out of these ends, but I think what I prefer to do is just rationalize the denominator right away. Square root of 5n cubed over the square root of 5n cubed. Okay. In my numerator, I'm going to end up with square root of 3 times 5 times n times n times n times n. In my denominator, I'm going to end up with a 3 on the outside, because we do the integers first. 3 times that invisible 1. And then in my radical, I've got